Welcome. In the context of manifolds embedded in an ambient manifold, I want to come back to an older story, the story of Wu characteristic, which is a higher order invariant like the Euler characteristic. The Euler characteristic just counts simplices, super counts simplices, and the Wu characteristic is more sophisticated in that it also looks at the interaction of simplices. So it looks at pairs of simplices which intersect. And it's not a homotopy invariant. You can just compute it for different kn, for example, complete spaces, complete simplicity complexes, and in that case it just depends on the dimension. It's -1 to the d, where d is the dimension. So a zero-dimensional one has 1, a one-dimensional complex has -1, and you can just count these interactions. It also comes with a cohomology, which, like simplicity cohomology, is very basic and very down to earth, using this idea of Ekman to look at the Hodge story. So you write down an explicit matrix, D, which is an exterior derivative, then you have a symmetric matrix, Dirac operator, and this allows you to then define cohomology as the kernel of these blocks, of these Hodge blocks, and the dimension of these kernels are the Betti numbers. So these are invariants under barycentric refinement, topological invariants, but not homotopy invariants. So it's kind of an interesting story, but it's expensive to compute this. And one of the impediments I had so far here, just to compute it for complements of knots, that's where I really want to go, is that the matrices are just too large. The matrices grow very, 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 very fast here. So you have a chain complex like in simplicity cohomology, but you look at the pairs of simplices which intersect. So there are much more of them. So it's like not quadratic, but it grows sufficiently fast that you quickly get into the limit of what a computer algebra system can do. I have here just put together a couple of things. Some of it I have known, like this is kind of a cool result which tells that for a manifold with boundary, then we have the Wu characteristic is just the Euler characteristic of the manifold and minus the Euler characteristic of the boundary. So that explains also a little bit here. So in this case, the Euler characteristic of this manifold with boundary, so to speak, is 1, while the Euler characteristic of the boundary is 2. So it's 1 minus 2 gives you -1. So that's holds for any manifold with boundary. I mean, this is something actually almost trivial, and it's just counting simplices. If you look at the Wu characteristic of a space, this is very general, and you look at then you can look at all the pairs of simplices which are in A, and all the pairs of simplices which are in B, and then you can look at all the pairs of simplices where one is in A and one in B. This is kind of like an interface. And if you count, then they have to be in these 3 cases. So that's kind of almost obvious. It's just a counting. But it comes in handy if you look at manifolds. And if you look at manifolds, then we can look at this interaction energy. So what we have is, when I'm looking at SAR, what I have at first, I have just an open set here as my level surface. Level surfaces are just all the hypersurface, for example, is all the simplices where the function changes sign, right? And then we have that, and then you make out of it a manifold. And in this case, we can say something about this interaction energy. It's actually just the interaction energy of the boundary of the, is not complement. So in this case, these are just tori, right? Topologically, the boundary of K, of the complement of the knot, is a tor, so it's 0. So in this case, this interaction is 0. Actually, if both K and T have to be even so that you get something interesting, then you get just 2 times the Euler characteristic of the manifold which you embed. So this is a 2 manifold. This is even-dimensional manifolds, you have a chance that this is not 0. So that's kind of one remark which just follows directly from the counting, but I did not get much into the cohomology yet. And one of the difficulties is also that when you're looking at these embedded manifolds, they are not necessarily already nice. And I looked at the example of let's just look at the example of I looked at the example of the icosahedron I last time glued together this with this. So to produce here, when I take this off and this off, I get a cylinder. I glue two such cylinders together to a torus. So that was a kind of a cheap construction of a 2 torus, which can be done in high dimensions too. But if I would have chosen a case where the 2 triangles are close together, then the complement K, which is this minus this 2 open, which is the union of these 2 open sets, which is an open set, would be close but not a manifold with boundary. So what we need to do is, in order that this is really kind of working nicely, we need to refine that first. One of the possibilities, kind of a simple possibility here, would be just to take this triangle identified with one of the triangles in an octahedron and just glue that in. So I drew that here. That's actually an octahedron glued in. And you glued in an octahedron here also. It's kind of like a local refinement. And what happens now, these 2 triangles are now nicely separated, and the complement is a manifold with boundary. So that's kind of something which needs to be done if one wants to do the computation. And so I have still to implement this. And I don't want to do the barycentric refinement. That would also be a possibility, but that would be just too expensive. You could not handle that computationally. Now, I already started, to look at this BKs. In most if I take a random manifold, these BKs are quite interesting, but it's also interesting just because the manifolds are not yet really nice enough, meaning that the complement is not the manifold with boundary. And this really matters in the interaction thing, right? In the interaction cohomology, you have this kind of more subtle thing. So you have also interactions between 2 simplices, and not just a simplices by itself, like what you have in Euler characteristics. I have here also again given the definition of a manifold. You can do the definition of a manifold just in terms of graphs, and if you have a simplicity complex, look at the corresponding graph. That's a cheap way to do that, but here is you can also do that directly in the context of simplicity complexes. And you could do that also in the context of delta sets, which is the ultimate framework you want to work with. And also all this cohomology here works, for delta sets. The only thing you really need a notion of when 2 sets intersect. I want to see now just first to see how I can do that within the framework of graphs or simplicity complexes, and whether this is actually working. I mean, it's very interesting, this invariant. I gave once a math table talk here. One prototype example which I have looked at, one of them is you take the cylinder. So you can write down explicitly this matrix, and you can look at the cohomology. So there is the second and the third cohomology is not trivial. While if you take a Möbius strip, you take that, but you identify it the other way around. If you take a Möbius strip, then for a Möbius strip the cohomology is trivial. But so they're also homotopy equivalent, right? You can just shrink them to a circle, both of them. But the cohomology is different from this and this. If you are looking how it is embedded, you don't look at the manifold, you look at the complement. And so that's what we do here, we look at the complement. And just very nicely, this manifold which we have is actually an open set, so that the complement is closed. We don't have to do any of the tubular, neighborhood constructions, which actually I did before when I was studying, trying to find that for a knot, for example. Take a curve in, you know, a triangulation of space and look at the, you know, make it fatter and then take away the boundary. It's just too large. The matrices are getting too big. Now I hope with this that it is going to work. But we will see. Maybe in spring break I will have some time to look at that. That's it for today.